Hi class, this is the last section of 13.10. This is osmosis. Why drinking salt water will cause dehydration, and we're going to look at that. So in osmosis, water flows from a lower solute concentration to a higher solute concentration. So think of it as it's diluting the higher concentration of something. The level of the solution with the higher solution will then also rise because of the additional water molecules that have went into that solution trying to dilute it out. So the concentration of the two solutions will become equal in time, but for a while the one will be higher than the other. And what this picture is showing is if there's a semi-permeable membrane, it allows some of this to go through but not other things to go through. So water will flow excuse me, so won't allow the sucrose particles in this solute, for instance, cannot pass over to this, but the water molecules will be able to pass in, and that will cause this side to go higher. That's what the difference in the water levels is osmotic pressure. The more solute particles, the greater the pressure is, because more water molecules will keep going over trying to dilute this solution. So here is why seawater or salt water makes you thirsty. As it flows through the stomach and intestines, seawater draws water out of the body tissues that are already hydrated. So it's pulling out the water from those organs in order to dilute the seawater that is highly concentrated. So even though you're trying to not become dehydrated, you're actually becoming dehydrated because it's forcing water out of other tissues to reduce the concentration of this concentrated solution, if that makes sense. So for instance, it's more concentrated with sodium chloride solution here, and outside in another organ, outside the intestines, it's not. So in trying to hydrate yourself, you're actually dehydrating other parts of the other organs by it's going to try to dilute the solution here, but it'll have to dehydrate other organs. So this is excuse me, this is called a U-shaped, I lost my notes on it, sorry. This is a U-shaped tube, and this can show you an example of what happens with osmotic pressure. So a U-shaped tube is separated by a semi-permeable membrane into two sections. And what can happen is that the water molecules can pass over here, but these blue particles cannot pass over here, so they're stuck in this one side. And so the water molecules on the right and the solute and water molecules are on the left. The initial state, which is the first part drawing here on the left, shows water levels are equal in both sides. But eventually what will happen is that water molecules, it'll go in equilibrium where these water molecules will start going over and some will come back. But it will try to access, so at equilibrium, water molecules have moved across the semi-permeable membrane toward the solution with solute particles on the left side, which ends up with a higher water level because it's trying to dilute that concentrated amount of particles by adding more water to it because it's concentrated solution. And the difference in the water height between the two arms, that is the osmotic pressure. So the more particles are here, the higher the difference is going to be because it's going to pull more and more of the water molecules over to try to dilute the concentrated solution. So osmotic pressure, like freezing point depression, boiling point elevation, is a colligative property. It depends only on the concentration of the solute particles, not actually the type of solute particle, not the type of solute. The more concentrated the solution, the greater osmotic pressure because water will keep trying to go over and dilute it more and more. The membranes of living cells act as semi-permeable membranes. So if you put a living cell in seawater, it will lose the water through osmosis and dehydrate it, and it will become weird shaped looking, which is what we're going to look at next. This is a slide from another section of chemistry. So these words are not in your book, but this is the terms that for it. So we have normal, which is just an isotonic solution, which allows the red blood cell to retain its normal shape, volume, and how it looks. Nothing's causing it to be dehydrated or overhydrated. Hemolysis is a hypotonic solution. Water flows into the red blood cell, causing it to swell, and eventually it'll burst. So it becomes really big. So you can see here, these have like little Cheerios, and these do not look like Cheerios. And then these weird ones, these little star-shaped ones, these are crenation. In a hypertonic solution, water leaves the red blood cells, causing it to shrink, and it gets that weird puckered look. So this is just pretty much going over each page. It's telling you this. The solute concentration of this is equal within the cell and the solution. So there's no osmotic pressure happening, and the red blood cell allows it. It will keep retaining its shape. Here, a red blood cell starts to swell, and that is because of the fact that a cell is placed in pure water, and osmotic flow of water into the cell causes it to swell up. So it's trying to balance itself, and in the process of doing that, it eventually causes the cell to burst. And a cell is placed in a concentrated solution of osmosis, and it draws water out because it's trying to, it's pulling any of the water out of the cell, and that's where it gets that pucker, dehydrated look. So review solution concentration. 3 common ways to express solution concentration are mass percent, molarity, and molality, which is what we just covered in 13.9 and 13.10. Freezing point and depression and boiling point elevation. A non-volatile, which does not vaporize easily, will extend the liquid temperature range of a solution relative to the pure solvent. So think of the pure solvent as water and know those temperatures. And when we add something, it will change those by either increasing or decreasing, depending on what we want. Osmosis is the flow of water from a low concentration solution, which is diluted, to a high concentration solution through a semi-permeable membrane to try to dilute that high concentration.